Changes now.
Yeah, we're very happy to have Professor Rahul Santhanam from the University of Oxford, who's better known to hold a chair in the School of Technology and Computer Science that has just been vacated. Nothing to do with this. So anyway, yeah, Rahul is a long-time friend of the school. He is a complexity theorist, really a broad complexity theorist, works in various areas, and he will talk about generative dimensions.
Thanks. So these green and red switches are all equivalent, right? They all involve the same.
Yeah. I mean, all reds are equivalent, all green.
Sometimes. Okay, so the title of this talk will be how to construct random strings. This is based on joint work with Oliver Korten. So let me kind of tell you what the motivating question is. The motivating question is is explicit constructions of countable objects. So something that's of great interest in combinatorics, in complexity theory, in many different fields. So what do I mean by explicit construction? So we have in mind some property Q of Boolean strings. We'll be thinking of many different kinds of objects to construct, graphs, matrices, Boolean functions, etc. But they'll all be represented as Boolean strings. And what is an explicit construction? So construction is, so we say that Q has explicit constructions. If there is a polytime algorithm A, which if Q has some string of length n, generates a string in Q of length n, such that A of 1 to the n. So if if Q is non-empty at length n, then A actually generates something from Q. So A of 1 to the n is in Q in say C1 to the n, right? So we have an explicit, so we have a polynomial algorithm, an efficient algorithm, which generates objects in Q. And there's sort of let's also consider a relaxed notion of this. So let's say there's a list explicit construction. Q has, or maybe I'll just modify this definition here. So let's say it's a list explicit construction. If instead of constructing a single object satisfying Q, you construct a set of objects such that at least one of them satisfies Q. So instead of this condition here, A will now be a set, and you'll have that A of 1 to the n intersect Q intersect 0, 1 to the n is non-empty. So this will be a notion of explicit construction. So in polynomial time, we want to construct some object satisfying Q.
Okay. This list should be poly-sized, or
yeah, because A is polytime.
So the list it should be it should actually write down. It can't implicitly output a list.
Oh no, yeah. So this set is sort of like a set that's explicitly written down, and then it has to intersect Q. Yeah. So yeah. So this implies that there's some polynomial set of objects that you construct efficiently, such that at least one of them belongs to Q. So let's see which is the right way. So now we look at some examples of properties Q for which we might want explicit constructions. And then ways in which we might go about trying to achieve explicit constructions. So the examples, so we'll have some sort of running examples in mind. So examples. The primes, rigidity, the Ramsey property, and the hard Boolean function property. So let me kind of talk about each of these in turn. And yeah, interrupt me at any point if there's questions. So yeah, primes is of course very straightforward. So primes is just a set of n such that n is prime. So the first approach we're going to try in terms of constructing objects explicitly is by pseudo-random generators. And when one way or another, pseudo-random generators will be involved in all of the things we say. But there's an obvious way in which they can be used, and that's what we'll explore first. And when we're exploring that, we're interested in two things. We're interested in how dense these properties are. So for each of these properties, we're interested in the density of the property, what fraction of Boolean strings of length n satisfy the property, and we're interested in the complexity of deciding the property. What's the best kind of complexity upper bound we have in the property, right? So let's just, as we discuss each property, say what we know about the density. So primes, by the prime number theorem, the density we know is omega 1 over n. And the complexity, well, by the AKS result, primes is in P, right? So there's a polynomial time property which has density that's 1 over polynomial, and so that's reasonably dense, and it's in polynomial time. Okay, now rigidity. So let's say
n is being used in all sorts of ways, you know.
Sorry. Oh, sorry. Oh, yeah, it's being used. So maybe
change that to
yeah.
P is a prime, and this is n, which is n bits.
Sorry. No, I mean, let's just say n for the prime, and let's just log n here. The length of n. Yeah. Yeah. So there's two different n's. There's the input length here, and this is. Oh, you prefer to have n for the input length uniformly. But yeah. Okay, and then so the second property we'll consider is rigidity. So let's define rigidity. So we'll only be considering rigidity over like matrices over F2. So we say so first of all, let's say that matrix A, the weight of a matrix A. So let's see. The weight of A is just a number of non-zero entries. And we're going to say that matrix A in F2 to the n cross n is, let's say, R L rigid if there does not exist an A and B such that A is the rank R matrix and B is the matrix of weight L, such that they add up different. Oh, so yeah, we need to say B and C. Such that rank of B is less than equal to R, weight of C less than equal to L, A equals B plus C. Okay. So you can't express A as a sum of a low rank matrix and a low weight matrix. Okay, so that's what rigidity is for us. And rigidity is sort of like a notion that's also been very well studied in complexity theory from the 70s, because it was first defined by Valiant, because like constructing matrices that are rigid with, so if R is like so n over log n, and L is like n to the 1 plus epsilon, and you get like an explicit construction of rigid matrix, then you actually get some low bounds for certain kinds of like linear operators. So you get like linear operators that are explicit that can't be computed by log depth linear size circuits. That's the original motivation of Valiant. Since then, there have been many other applications and connections found for rigidity. I mean, I guess Renaud's worked on quite a bit. So this is a big kind of open question. And actually, I mean, yeah, so there's some sort of results known in terms of constructing such matrices in P to the NP, not explicitly, but with an NP oracle. And Rahul, for example, has some joint work on that from a few years ago. So this is the second property. So what about density and efficiency here? So density, well, I guess it depends on what R and L are, but there exists an epsilon for which the density is 1 minus little o 1. So there's a simple probabilistic argument. So if you pick, so think of yeah. So what are R and L? So R is going to be epsilon times n, and L is going to be epsilon times n squared. So epsilon n, epsilon n squared rigidity is going to be it's going to have density 1 minus little o 1. And that's just a probabilistic argument where you think about how many possible pairs of matrices are there, B and C, such that B has rank at most R and C has weight at most L. I mean, if B has rank at most R, then you can describe it as a product of two matrices, each with n times R entries. So that's 2 times n times R bits. And so it's 2 to the 2 nr. And then this is like n choose less than or equal to L. And if you multiply those, you'll see that there exists an epsilon for which this is less than 1. So it's just a kind of straightforward probabilistic argument. So this is very dense. And how about the complexity? Like what's the best sort of complexity upper bound you think can be achieved for rigidity? Yeah. So if you look at this kind of expression here, right? So this says for all B and C, such that the rank of B is small, the rank of C is the weight of C is small. A is not equal to B plus C. That's easy to check that A is not equal to B plus C. And these conditions are easy to check too. So it's just a for all quantifier or B and C. So that's a co-NP predicate, right? So the complexity is so yeah. So for any sort of like R and L, which explicit or R rigidity. You can co-NP. And in fact, all of the properties that we consider will either be in P, like primes, or they'll be in co-NP. And then there's the Ramsey property. So for Ramsey, I mean, of course, there are many different kinds of Ramsey graphs. We'll just consider a simple kind where we consider simple graphs with some fixed bound the size of a clique and independent set. So we'll just say that a graph G on n vertices is K Ramsey if G does not have clique or independent set size K. And Erdős proved famously that there exists 2 log n Ramsey graphs on n vertices. And this too is by kind of simple application of the probabilistic method. You just sort of like take like a union bound over like all possible like cliques and independent sets, and yeah, you get a simple expression which when K is at least 2 log n, you get that the probability of the graph is not K Ramsey is less than 1. So here again, like the density is going to be 1 minus little o 1, as long as as long as K is going to be greater than, let's say, 2 plus epsilon log n. If K is 2 plus epsilon log n, then the density is close to 1. And again, the complexity. Well, I mean, the obvious way of kind of like solving this is to check for all cliques and independent sets, right? So if your parameter is like, say, 3 log n, then you can do this check exhaustively in quasi-polynomial time. So you could do it in time n to the order log n. But if you want to restrict yourself to polynomial time, but allow like quantifiers, then you can do it in co-NP, right? You just need to check for all vertices, vertex sets of size at most log n, that the vertex set is not an induced clique or independent set, right? So for every subset of vertices of G, it's not a clique or an independent set, right? So that's a co-NP check again. So this is again in co-NP. Is that clear? Can anyone think of like complexity theoretic reasons why this cannot be done in P? I mean, any sort of thoughts on why you should not expect this to be in P? Is that like a standard complexity theoretic conjecture under which take 2 to 3 log n Ramsey is not in? So there's like the planted clique conjecture, right? So the planted clique conjecture says that you can't distinguish between a random graph and a graph with a large random planted clique in it. But of course, the graph with planted clique in it is not Ramsey, and a random graph is. So just the fact, so this conjecture, the planted clique conjecture, implies that Ramsey is not going to be. The planted clique conjecture is stronger than saying Ramsey is not going to be. So that's at least some reason to believe that you can't do better than CoNP for polynomial algorithms. Okay, so finally, hard Boolean functions. So let's say that.
Sorry, so can you just repeat what was the planted clique conjecture?
Oh, so the planted clique conjecture says that if you can't distinguish between these two different distributions, one is the GN half, so a graph kind of sample uniformly random with each edge sample property half, and GN half, but with a random subset of vertices, like even of size, say, n to the 1/3, which is chosen, and a clique is placed on that, right? So there's some kind of big clique embedded in this graph, but you can't really tell that it exists. You can't really distinguish this graph from a random graph. And that's a conjecture that's been sort of used to kind of show hardness for many other problems. It's been investigated extensively. Yeah. Okay, and finally, the hard Boolean function example. So like say, given parameter s, yeah, so n Boolean function f is s hard if it does not have Boolean circuits of size s of n. Where n is the number of variables of this Boolean function. And by counting arguments, we know that even s of n equals like 2 to the n over 3n, that there exist Boolean functions which are hard for that parameter. So even for s of n equals 2 to the n over 3n, let's say, there exists f that is s of n hard, and most f are going to be s of n hard for this parameter. So for this parameter, again, the density will be 1 minus little o1. And the complexity. So yeah, this is just repeating sort of like the theme that's gone before. So how do you check that? So if it's, consider this Boolean function to be given by its truth table, right? So the Boolean function is on n bits. So it's an n-bit Boolean function, but it's given by its truth table of size 2 to the n. So that's a big object. How do you check that that has no circuits of size s of n for say s of n equals 2 to the n over 3n? Well, the obvious way is just to check, try all possible circuits and see if they compute the function. So the check would be for all c of size at most 2 to the n over 3n, c does not compute f. Right? And this check that c does not compute f is actually efficient. It's actually polynomial time because you have the truth table of size 2 to the n given to you. And you can just evaluate c on every possible input and check that there's some input on which the circuit fails. Right? So this is a for all quantifier and then a polynomial time check. So that's a CoNP computation again. So yeah, all of these problems have in common that they're in CoNP. And the last three are all dense, right? So in this case too, you have like as the circuit size parameter goes down, that little o1 gets really, really small. So it's a very dense property. Okay, so when you have like problems of this sort, there's a pseudo-randomness based approach that you can try for deriving explicit constructions. I mean, these are problems of very different kind of character, right? I mean, like there have been approaches to showing that graphs are Ramsey, to constructing explicit Ramsey graph, very graph theoretic approaches. Rigidity, you'd like to use linear algebra to show that a Boolean function is hard. Well, you can try many different things, none of them work. But yeah, so there's these come from very different kind of domains, and there are different approaches used for them. But they have some kind of properties in common. I mean, there's the density and the complexity, and just by leveraging these properties, we can say something that's interesting about explicit constructions for these properties. Okay, so let me just remind you, because I'm sure you've all seen this before, what a pseudorandom generator is, and then I'll show you how to use it in this context. So definition, say G, let's have some parameters we define. So let S be the seed length, and epsilon be an error parameter, and let's say C is a complexity class, or class values. Let's just say class values. So we want to define the notion of pseudorandomness. So we want kind of like a generator G, or generator G is just a sequence of generators Gn, and each Gn is from S of n bits to n bits. And we want the output of Gn to look random. And what does it mean? It means that the probability for all A in C, so for all algorithms that come from this class of algorithms, the probability over y in 0, 1 to the n, A of y, minus, or A of y plus 1, minus the probability over z in 0, 1 to the s of n, that A of g of z equals 1. This property is at most epsilon of n. Okay. So, and we want G to be computable in polynomial time. So polytime computable G. Polytime let's say in n for now. So let's say it's polytime computable in n. So this is what an efficient PRG is. It stretches S of n truly random bits to n pseudo-random bits. And what does it mean for this distribution that's induced by Gn to be pseudo-random? It means that it's indistinguishable by algorithms from this class C, right? So this is what it means for G to be pseudo-random generator against C. So for every algorithm in C, the algorithm cannot distinguish a purely random string from a pseudo-random string. Okay? There's sort of like very interesting kind of like line of works in pseudo-randomness, which give very strong pseudo-random generators based on hardness assumptions. So theorem. This is due to Nissan-Dickerson and Parser-Dickerson. Under standard circuit low bound assumptions, so if E doesn't have circuits of size 2 to the epsilon n, even infinitely often, then there exists explicit PRGs with seed length order log n. Against polynomized Boolean circuits, but let me, in this, just thinking of what will come later in the talk, let me say for all k, there exist pseudo generators against time n to the k with n to the k bits of advice. Right? So this is the same thing as saying that there exist generators against Boolean circuits, pretty much of size n to the k, but I'd like to separate out the uniform complexity of the distinguisher of the algorithm from like the non-uniform aspect, the advice that it has. So this is kind of, these could be just uniform algorithms that you want to fool, or they could be non-uniform algorithms where you get some advice and you want to pull the algorithm together with advice. And the Nissan-Dickerson, Parser-Dickerson framework actually gives you pseudo generators against non-uniform algorithms. And then there's a version of this which works even against like co-NP algorithms. And we are particularly interested in co-NP algorithms because of the properties that we've been discussed before, that they're complexities in co-NP, right? So we're interested in pooling properties that are in co-NP. So if, and this is these results together with Cliven's van Melkewijk, if E is not an IO size to the NP, so if instead of having exponential circuit low bounds, you have exponential circuit low bounds even against a NP oracle, so even against circuits with an NP oracle, which is pretty standard complexity assumption, then you have exactly the same as before, except that now you're able to fool d time into the k with an NP oracle and advise into the k. So this definition of PRG is clear, and what these theorems are saying, is that clear? And if there's something problematic with the notation, just let me know.
What was size to the NP?
Size to the NP means that you have a Boolean circuit, and the circuit doesn't, usually it has AND or NOR gates, but it also has oracle gates where it can make queries to an oracle and NP, like SAT. We can just take without a last generic say SAT. So these are circuits which also make queries to SAT.
Then why was what is the role of NP over there? Were they able to show that exactly that it's the whole thing relativizes, that's all.
Yeah.
You could have just put in any.
Yeah. So there's nothing special. In fact, we can say P space here, and then this would be P space, any oracle, in fact. Yeah. It's just that, it's often useful to have PRGs against this class, and that's why, and that's how it's mostly used. But there are kind of stronger results you can get from stronger robot. So now there's like kind of like an obvious approach to explicit constructions that comes up, which is that, okay, you have all these properties which are dense, so which for many strings satisfy the property, and it's not too complex. So there's complexity upper bound on deciding these properties. So why not kind of like try to get explicit constructions via PRGs, right? Taking the range of the PRG, and instead of having 2 to the n possible objects, now we have only 2 to the s of n possible objects, and if s1 is order log n, there's polynomial in n many objects. And you would expect, since this is a PRG, that the probability that one of these poly of n objects satisfies the property is approximately the same as like the original property that a random object of length n satisfies the property. And since a random object of length n satisfies the property of probably close to 1, you expect the same now of this poly n size set, right? So in particular, you get from this immediately list explicit constructions, right? So this immediate probability of this is so probably pretty much is that if Q is dense and Q in co-NP, then under standard complexity-theoretic assumptions, and by standard assumption here, I mean the Kleibans-Van Menthe assumption that E is not I or size to the NP of 2 to the epsilon n, then under standard hardness assumptions, Q has a list explicit function.
The density is just that it has to be higher than the error of the.
Yes, exactly. Yeah. So you basically need that the density is greater than the error, and I mean the density is 1 minus root of 1 for these cases. The error you can actually, so I didn't say what the error was for those constructions, but you can take the error to be 1 over n, so it's actually quite small. So so in fact you'll get that most of the objects in this poly-size set are going to satisfy the property, but you don't know which ones, right? So for primes, actually, you get an explicit construction, right? Because you have this list explicit construction, and you can just check every object in the list to see whether it's prime or not, and output the first one that is. Because primes is in P, you can do this. So because primes is in P, this kind of argument also gets you an explicit construction under this assumption. In fact, under the weaker assumption that E is not an IO size to the epsilon n, because you only need kind of the PRG to work against deterministic or circuits. So for primes, you get an explicit construction, but what about all these other properties, right? So you have the set of candidates for explicit constructions, but you don't know which is the right one because they're in co-NP to check, and you don't know which of them satisfy a property. So you have polynomial list. If there was a way, given like 2 objects that satisfy the property, to output the one that did, then you'd be done. You could just kind of iterate and go through the list and figure out which one of the objects did have the property. But we don't know for any of these properties that we've seen before, for rigidity or certainly for rigidity and Ramsey, we don't have any such selection mechanism. So we just have this list, and we don't know how to get a single object from it that satisfies property. So is this totally clear? I mean, any kind of questions about that? So that's somehow like, yeah, it just follows from previous results. So just trying to recap what's known already. And I should say too, if Q is dense in P, then there is an explicit construction. Again, understand the assumptions, there exists explicit construction. And in particular for primes, there is. So yeah, we're not going to worry about primes anymore because there's some standard complexity assumption under which we have explicit constructions. We're going to worry about all these other properties. And in fact, for most reasonable properties, I mean, even the property of being good at interpreting code, these tend to be in co-NP, not in P. So for most properties we're interested, they're in co-NP. So it's not clear how to get an explicit construction for these properties. So what we're going to do is we identified these two criteria, right? Like the denseness and the complexity. And we saw that those together were enough to get these list explicit constructions, but not get explicit constructions. But perhaps we can look at the proofs of existence of these properties and try to extract more information that will allow us to get stronger results, right? To get explicit construction or just less explicit construction. So are there other sort of criteria that you can use? So the first thing we're going to do, and this corresponds to like work that was done just a few years ago, is to look at how the probabilistic method is actually applied and show that actually it gives something more, right? So so suppose you have like yeah.
So if you're in Q, there's one more property of Q which you mentioned is a set of hard functions.
Yeah.
So you're having this hard function assumption, you're outputting a hard function. So how do the quality of these two differ, or these are two very different?
No. I mean, you just get back this. I mean, it's a trivial result. You won't get anything interesting for hard functions from it.
No, but do you lose something in the process? In the upper bound, you actually had the hard function with Saturn.
Yeah.
Also, you had an upper bound. The same thing is true of the hard function.
No. So you lose something, but for hard functions actually, you have a set of a list of them. At least one of them is hard. But there you have a way of like getting a single hard one just to concatenate the truth tables. So if you concatenate the truth tables of many functions, one of which is hard, you'll still get a function that's somewhat hard. So so that way you get a single object actually in that case. But as you say, it's weaker. I mean, you started off with an assumption about like NP oracle hardness, and then you're getting something, that's weaker. So it's not very interesting for hard functions. Yeah, right. So I guess we're going to be more interested in how like these complexity-theoretic assumptions apply something for combinatorial properties. Yeah, but the hard function example is a good one to keep in mind for later in the talk. Any other questions? So let's just look at this density property again, right? So let's say that for some parameter, so let's say we have a property Q, and let's say that the density is say 1 minus 2 to the minus so C, let's say, right? So that means that for a random object that satisfies the property with 1 minus 2 to minus C, that means that objects that are not in Q, so n bit strings that are not in Q, there's only a 2 to the n to the minus C of them, right? So in principle, these objects that are not in Q can be described with n minus C bits or close, right? So they're in principle they're compressible, but it's not a priori clear how to efficiently compress them. So what we're going to observe is that with these kind of properties that we have, there's actually a way of generating the entire description of an object not in Q from a small kind of a compressed representation of it, right? And it's quite easy to see with Ramsey especially, but also with rigidity. So I'll kind of just like describe to you how that works. And that will be the basis for a new definition of this problem called the range avoidance problem. And that, will, I guess, give us a new approach to try to argue for explicit constructions. But let me kind of like first give you examples. So for Ramsey, so let's take the K-Ramsey property. So what do we want? We want to describe succinctly those objects that are not K-Ramsey. I mean, those objects that have a clique or independent set of size K. So how do we do that? So we do that by, well, first of all, there's a bit B. So this bit B is 0 if it's a clique and 1 if it's an independent set. That's just going to tell us is it a clique or an independent set. And then there's a set S, right? So this set S is going to be of size at least K. And it's going to be described explicitly. So S is just a set of vertices. So each vertex is from 1 to n. So can be described with log n bits. So S is going to be described with K log n bits. And then we're going to describe E minus S cross S, right? So E is all the edges that you have, but you're not going to describe the edges within S because if B is 0, it's a clique and everything in S is connected to everything else in S. If B is 1, it's an independent set and nothing in S is connected to anything else in S. How many bits does it take to describe these? Well, the n choose 2 possible edges, minus K choose 2. To describe S, it's K log n. This is just 1 bit. So 1 plus K log n plus n choose 2 minus K choose 2. When K is bigger than 2 log n, this is going to be less than n choose 2, right? So you're going to be able to compress graphs when K is bigger than 2 log n. So this immediately gives you like Erdős result, for example. I mean, it's a simple probabilistic argument, but the point is that now you can do this efficiently, right? From this description, you can kind of like get the entire graph G or n choose 2 bits efficiently using a small circuit, a polynomial size circuit. The circuit will give you the entire adjacency matrix of G by looking at the bit and deciding the edges within S appropriately, and then just copying from here for all the edges that don't have the limits.
So, you're describing the entire graph, right?
Yeah.
So,
No, but using less than n choose 2 bits to describe the graph.
So you want to describe those graphs that are not Ramsey using less than n choose 2 bits.
no, but he's telling me whether, he's telling me, I don't see this, I'm missing something, it looks very trivial.
Oh, so for S, the trivial way to do it would be to give you each edge, whether it's there or not. That would be n choose 2 bits, right? Here, the set S of vertices is sort of separate, right? So the set of S of vertices, you don't need to describe the edge relation within that set because it's either a clique or an independent set, and that's just one bit to describe. If it's a clique, then
No, I understand.
yeah.
This is essentially the proof of the probabilistic method proof.
Okay.
Yeah, but it's just that the probabilistic method proof gives you an efficient way to recover from this smaller description, every graph that's not Ramsey. So yeah, that's kind of the observation that's being made here. Yeah. Any
Well, the biject I think the probabilistic method proof is also biject, but it's like removing the probability.
Yes, exactly. Yeah.
You're just saying that these graphs have much fewer bits, so you can compress them.
Yeah.
Therefore, most graphs.
Yeah, exactly. Yeah.
All of them are described by fewer than n choose 2.
Yeah.
So they're
But described efficiently in the sense that there's a polynomial size circuit which from the smaller description can recover the graph. For every graph that's non-Ramsey, it can be recovered efficiently from a smaller description.
Or something you said earlier. So you said for the hardness problems, this gives something trivial.
Yeah.
But you said even if you had a list of hard like 2 tables of hard functions, the concatenation should also be a sort of hard function.
Yeah.
Just maybe I'm missing something. For rigid matrices, something like this is not true that you can't.
What would be the operation you use instead of concatenation? So
You
you
don't just have like them in a diagonal or something. Maybe it's too huge the matrix.
Yeah, if you're looking at the same input length, it's not clear what to do, but at different input lengths, I don't know. I haven't thought about it. I don't know what kind of parameters you get from that, whether it be anything non-trivial, but it's possible you get something. I'm not sure.
And a similar thing for non-primes will be just the prime factors.
No. So here's the thing. Non-primes, so primes are not that dense. They're only 1 over n. So you can't expect like a compressed representation like this, right? And in fact, like if a number is not square free, then it can be compressed. Because you can give like the primes and the prime factorization together, the exponents, descriptive exponents, that can compress a number. But if a number has only it's just a product of primes, then there's no obvious way to compress it. So primes together, the products of primes are very dense. And so this will be an efficient way to kind of like compress numbers that are not of that form. But it's not interesting to explicitly construct primes or products of primes because you can just output the product of the first log n primes, and that's good. Yeah, so this works when the property is very dense, and the last three properties that we looked at were all very dense. So yeah, and I just want to say that yeah, we can do something similar for RL rigid because you have like the rank R matrix, right? That's can be so matrix B, which is equal to say B1 times B2, where B1 is an n times R matrix and B2 is an R times n matrix. There's just 2 times n times R bits, right? So that's 2 times n times R bits. And then you have C, which is a weight at most L matrix. So that can be described by log of n squared, which is less than or equal to L bits. And so this is going to be quite a bit less than n squared, right? When you choose L and R appropriately. I mean, given B, B1, B2, and C, you can recover the non-rigid matrix A, which is B1 times B2 plus C, right? So every non-rigid matrix can be recovered in this way from a smaller description efficiently. So it's true of rigidity too. And it's true in kind of like also trivial way for the hard Boolean function case, because there the compressed representation is just a circuit, right? So the map that maps a circuit to the truth table of the circuit, this is going to be a map that gets you the explicit representation from the compressed one. This is for the hard Boolean function case. So what is range avoidance? So it's a very natural problem, which for mysterious reasons wasn't studied before. So you have a circuit from n bits to m bits, and we know that m is greater than n. The question is to compute like a non-output of the circuit, right? So yeah, if n is less than m, then at least half wall strings of length m are non-outputs of C, and you just want to deterministically compute one of these from given C. Okay, so definition, an algorithm A solves range avoidance. So let's call circuits of this sort expanding, meaning that their output length is greater than their input length. On an expanding circuit C, from n bits to m bits, if A of C is an m-bit string, not in range of C. Okay. So you just want to output something that's not in the range. You want to output some m-bit string that's not in the range, and this is the total function problem if m is greater than n. Expanding just means that m is greater than n. Yeah, because if m is not greater than n, then you don't necessarily have a solution to this problem. If m is greater than n, then you're guaranteed that there's a string outside the range, and in fact that half wall strings at least are outside the range. I mean, it's also total when you're mapping, say, 2 to the n objects to 2 to the n plus 1 objects, but there you don't have this nice kind of like density property that half wall strings in the codomain satisfy. So we want that density condition to hold. So with range avoidance, yeah, maybe the m looks too much like an n. So hopefully it's keep in mind that it's an n. Yeah, so there are different aspects that are important. One is the stretch, right? So the stretch is just the relationship between n and m. So the bigger m is as a function of n, the easier it is to solve range avoidance because, yeah, I mean, you've got to, yeah, most outputs are not in the range and you just want to find one. So the hardest case is when m equals n plus 1, essentially. So that's the hardest case. And the other thing is how complicated is the circuit C, right? So if the circuit C is an arbitrary Boolean circuit, maybe this is hard, but you could even consider like C being like an NC0 circuit, a circuit where every output bit only depends on a constant number of input bits. And there it might be a much more tractable problem. So yeah, how tractable the problem is might depend on the part of the class of circuit C that computes range avoidance instance, but also on the stretch, right? So so each of those problems that we defined before correspond to some stretch, right? So K Ramsey, for K that's like 3 log n, K equals 3 log n. This will correspond to stretch like n minus O with log n squared to n bits, right? So that's not very much stretch. But rigidity, even with parameters we don't know how to construct, has much bigger stretch. So you get something like n over polylog n bits to n bits. And the stretch would be even more with like the hard Boolean function example. I mean, especially if you consider smaller circuit sizes, like 2 to the 0.9 n, then you have like a much bigger stretch there. Okay, so in that sense, like something like the hard Boolean function example is, kind of intuitively easier case of range avoidance. It has a much bigger stretch.
So in K Ramsey, what will be the input here?
Oh, okay. So now so I've just so I gave you these kind of like decompression algorithms, right? So I'm going to think of like each of these decompression algorithms to be like a circuit, right? So each decompression algorithm from a compressed representation computes something that's not satisfying the property. So if you solve range avoidance for such an instance, that gives you explicit construction. So each of these kind of cases where I showed you like a decompression algorithm for the complement of the property, by solving range avoidance for the circuit that implements a decompression algorithm, you're going to be able to solve the explicit construction problem for the property. Okay? So that's the idea here. That
this is why you care about the complexity of this decompression.
Exactly. So I mean, we'd like to kind of show that the complexity is as low as possible so that the range avoidance kind of problem is sort of easier to solve. I mean, this might even give an approach to unconditional like explicit constructions, right? Like for example, for the Ramsey problem, it's a very, very simple sort of decompression algorithm where, I mean, like many bits are just getting copied directly. And in some cases, you're just sort of like checking whether like the say U and V are on the set. And if they are, then you're just having an edge between them. So that's very, very simple. So you might think that, just by
even for rigidity, it's very simple. Just
yes. Exactly. So those are both cases where the decompression algorithm is very, very simple. And one might try to take advantage of this and actually unconditionally solving it, even with our complexity assumptions. Okay. So is it clear what the relationship is between what I just said about decompression and range avoidance? So my claim is that like each of those decompression algorithms, essentially by thinking of the decompression algorithm as a circuit and solving a range avoidance for the circuit, you solve the explicit construction problem for the corresponding property Q. Right? So solving the range avoidance problem for this circuit that gives you that matrix from this description would give you a rigid matrix, an R, L rigid matrix, and solving it for that circuit there would give you a K Ramsey graph. Okay. So now, well, how do we solve range avoidance, right? So is it the case that under complexity assumptions we can solve range avoidance? I mean, here we are sort of like using some stronger property of these application of the probabilistic method, namely that they give you efficient decompression algorithms. And so maybe now that can be leveraged to give evidence for explicit constructions. Well, one thing you could do is to use the pseudorandomness method again, right? So you know that like a random string of length m is not in the range. And you know that most length m strings are not in the range. So the complement of the range, right? So if you take the subset of 0, 1 to the m, which is the complement of the range of C, that's a dense set. It has more strings in it. And what's the complexity of that set? It's again like it has complexity like co-non-term stick circuits, right? You just need to check for all z that C of z not equal to y. So if you want to check that y is not in range of C, you just need to check this, right? And so you just need to universally quantify over z's of length n and then evaluate C. So this is a co-non-term stick algorithm with advice. The advice is the C. So under hardness assumptions as before, you can get like a list explicit construction for range avoidance. You can get a list of strings such that at least one of them is outside the range, but it's not clear again how to select a single one. Now, if you allow in your kind of like your explicit construction algorithm the use of an NP oracle, then you can get like a an explicit construction, right? Because for each string that in your list, you check whether it's in the range of C, and if it is, you reject it. You know that at least one is not, and the one that is not, you output. So under standard complexity assumptions, you get a P to the NP explicit construction, but it's not clear how to get an explicit construction. Okay, so this was defined by Korten, Kleinberg, Mitropoulos, and Papademetriou, and then and then studied more by Korten, but it's
the range avoidance.
the range avoidance problem. Yeah,
So you're the one who gave the terminology.
So they're the ones who defined the problem. They didn't give the name range avoidance, but they defined the problem. Yeah.
Okay.
And then it's kind of applications were further studied by Korten. So there's been quite a line of work since then. But the sort of like the punchline is this theorem by IRW, Ilongo, Liu, and Williams, which is that under kind of certain cryptographic assumptions, so if NP is not equal to co-NP and sub-exponentially secure indistinct obfuscation. So this is a cryptographic primitive, indistinct obfuscation, one that's been studied quite a lot recently, and there's strong evidence given for it now. So in cryptography, I mean, you have many sort of like primitives like one-way functions, trapdoor functions, and so on. And indistinct obfuscation is quite really powerful primitive, and it's now been shown to exist under reasonably standard hardness assumptions. So if the standard crypto primitive, somewhat standard crypto primitive exists, and you have this complex separation, then there's no efficient algorithm for range avoidance. Even with polynomial stretch. So poly stretch is the largest stretch you could hope for, right? I mean, you're sort of like, you're stretching n bits to any arbitrary polynomial in n bits, and you still can't solve range avoidance. And actually, the hard instances they construct, so they show that under these primitives, there's a function where I think like, there's only like 2 strings in the output, and you can't solve range avoidance. So so it's a pretty strong result.
So what's I want to pass the statement. So does it say, given these assumptions, there is a range avoidance problem which doesn't have a good solution?
Yeah.
Or every range avoidance problem of a particular type does not have an efficient
No,
algorithm?
there is a range avoidance problem that
So
does.
it might be that the range avoidance we care for, all of them have a.
That's the next part of the talk. So these are kind of somewhat artificial instances, maybe one could say. So these instances don't have. I mean, maybe what this says is that range avoidance isn't like a sufficient abstraction for studying this and giving evidence for explicit constructions. But relatedly, there has been like interesting work on unconditionally giving algorithms for range avoidance and NP oracles. For example, it's known that there are polynomial times, efficient algorithms for every range avoidance problem with an NP oracle, a randomized algorithm, which outputs a fixed string with high probabilities, so-called pseudo-deterministic algorithms. So a randomized algorithm, which on most computation paths outputs the same string with an NP oracle. And this actually has given like lots of new circuit law bounds, such as the fact that ZPX with the NP doesn't have exponential size circuits or exponential size circuits. So that's other work that's come out of this, but somewhat orthogonal to what we are going to be discussing.
I and W is I is Ilongo, W is Williams, and L is Liu.
So this IRM does not imply that there are no efficient pseudo-deterministic algorithms.
No. There are. So you mean even without an NP oracle? It doesn't. But there's some follow-up work which says that under some kind of like crypto assumptions, there aren't even FNP algorithms. So algorithms that output like something that's non-range but non-deterministically. I mean, so range avoidance is something to check that something's not the range is core non-deterministic check, right? And so you can't even do it non-deterministically under some reasonable assumption. Okay. Okay. So what about these explicit construction questions? So so we're going to try to capture something that hasn't been kind of like moreover exploited so far, which is that like these decompression algorithms that I showed you, I mean, for Ramsey and Rigid, they, I guess, are not just range avoidance instances, but uniform range avoidance instances, right? So they're kind of like the circuits that do this decompression are uniformly generated circuits. So for Ramsey, it's like a fixed algorithm, polynomial time algorithm, which given like this compressed representation gives you a non-Ramsey graph. And for rigid matrices, again, it's like a fixed polynomial time algorithm, which given like this description of these two of this low rank matrix and this low weight matrix gives you the non-rigid matrix. So this kind of uniformity is being used, and the question is, can we exploit that to give evidence for explicit constructions? So somehow we're not interested in solving range avoidance in general for an arbitrary circuit C, but only for uniformly generated circuits. So we're going to try to exploit.
The construction of CLW gives you a uniform set, non-uniform circuit.
Of ILW, yeah.
Yeah, but the assumptions are uniform, even then.
So the assumption actually about industry obfuscation is against circuits. So this, yeah. So at this point, when I'm going to try to explore uniformity, it's kind of going to be easier and more natural to work with Kolmogorov complexity. So I'm going to just kind of like very briefly say which kind of Kolmogorov complexity it is. So I mean, basically, Kolmogorov complexity sort of captures, abstracts out how compressible strings are, right? And we're interested in this notion K superscript T. So K superscript T of X. So if T is a function from n to n, then this is the size of the smallest program. Is minimal size of P such that a universal program on program P generates X within T of size of X steps, right? So you want the smallest program such that from that program, you're able to generate the string X and at most T of size of X steps. So think of T as like a polynomial. We'll be thinking of T throughout as a polynomial on the size of X. So you're going to want to kind of construct X from its compressed representation efficiently, right? And if you think about Ramsey and rigidity and so on, like what we've shown is that that non-rigid matrices and non-Ramsey graphs have small k polycomplexity, essentially. That we give polynomial time algorithm for reconstructing non-rigid matrices and non-Ramsey graphs from small descriptions of them, right? So it turns out that it's solving range avoidance of uniform instances is equivalent to getting like strings of high KT complexity. So in a way, our question becomes, can we efficiently construct strings X with high poly X? And we're going to use techniques from Ceram generators again. That's pretty much the only thing we know how to do. So all we can do is try to construct better PRGs and use them. But
why did this have to go through the read? So this wasn't so like all the non-examples have small. So anything.
Yes, exactly. See, it doesn't. You're absolutely right. It doesn't have to go through range avoidance. In fact, it's easier to see just from the examples themselves that they directly have. I mean, like in general, it's true that uniform range avoidance and constructing strings is kind of like equal, but you lose a little bit. And doing things the way you mentioned by looking at the examples directly, you lose less. So it's better. Okay, yeah. Yeah. So So I guess what's being said is that we've actually directly shown in our examples that non-rigid and non-Ramsey have small k polycomplexity. We don't even have to go through uniform range avoidance. So this is going to be a task now, and I'm just going to say what the obvious approach using pseudo-randomness is, why it doesn't work, and then what we've got to do to improve on that. So what's the obvious approach using pseudo-randomness? So again, you have some pseudo-random generator O of log n to n bits. And let's say what we want to construct now is like an X that's that has high K poly of size of X complexity. I mean, I'm being a bit vague about what high is for now. Let's just say it's at least n over 2 or something, where n is the size of X. We won't be able to quite get that, but yeah, let me just say that for now. So one obvious way that you could try to do this is, well, you look at the set of strings of high K poly complexity. This is again a dense set. I mean, the strings that have small descriptions, there are very few of them, right? There are at most 2 to the n over 2 plus 1 of them, right? So random strings have very high K poly complexity. So it's a very dense set. And it's again a co-NP set, because to check that a string has high complexity, you just need to check that no small program can compute it. So for all small programs, you run for a fixed polynomial amount of time doesn't compute that string. That's a co-NP check. So we can again use a generator against non-termstic computations. So that's going to give you, so this generator, the Clemens-Van generator, which maps O of log n bits to n bits, that's going to have in its range, most strings in its range are going to have high K poly complexity, right? But yeah, oh, I see, okay. Yeah, but the issue is that how do we now get a single string? We can use the concatenation idea, right? So let's say there C log n is the C length here. So we have these n to the C strings, y1 to y n to the C, each of length n, and the concatenation of these y1 concatenated with y2 y n to C is a string of length n to the C plus 1, which one might imagine has high K poly complexity, but what's the, I mean, can anyone see what the issue is with doing that?
We'll take that further. So we are going to take this particular, so suppose you are given such a function. So where are we obtaining y1 through y to the C from?
The generator.
Outputs of the generator. The outputs of the generator.
Oh, okay. Just consider all the outputs of the generator.
By definition, cannot have low, it has low polynomial complexity.
No, because you're saying okay, you're saying because it's computable in polynomial time.
But the constants are different.
Yeah, exactly. Yeah, the constants are different. But yeah, I think like you're close to the answer, which is that I mean essentially the string is so long, it has n to the C plus 1 length, but it's only hard against like time t, which is smaller than n to the C, right? So for the generator to work, you need like C to be bigger than D, where D is the time required to check that a string is K poly hard. And so you'll get like a long string, but this will only be K n to the C over 2 random or something. So it's not very useful at all. I mean, you want a string that has high K, say n to the 100th C complexity, but you're only getting something that has K n to the C over 2 complexity, and it's longer, right? But typically you want like the time bound to be bigger than the length of the string that you're producing. But here your time bound is smaller. And this seems to be like inherent here because of the problem of the seed length of the generator. So the seed length of the generator is at least going to be logarithmic in the output length. And that's unavoidable if you're dealing with non-uniform classes that you're trying to fool. So I guess the main kind of like contribution we make is that we have like this hardness assumption. So let me just like mention the hardness assumption and then the conclusionary complement. So what's the hardness assumption? So assumption so there exists an epsilon. Such that for all time constructible D. So we'll be using here like iterated exponentials and logarithms. So yeah, let me just, I think you might already know what it is, but x0 of x is x, and x to the I of x is just 2 to the, let's say n instead. So the zeroth order exponential is just the identity, and then this is just 2 to the x to the I minus 1 of n, right? So iterated, so just a power of exponentials, and similarly you can do the logarithms, so the iterated logarithms. And then you have log here instead of iterated exponential. So if you have time bound, that's that's most an iterative exponential. There exists a function f, which from let's say n bits to n bits. Oh, let me just actually say 1 to the n. So there is a function that on f of n essentially is an n-bit string, and f is computable in time t. But not in time t to the epsilon with an NP oracle, even with n to the epsilon bits of advice. So it's just a generalization of standard circuit of hardness assumptions. So general hardness assumptions are about t being polynomial. If you think about computing the truth table, it's essentially corresponds to t being polynomial. And here you're making the assumption for larger constructible bounds as well. If you didn't have this NP oracle, this is just unconditionally true for large time bounds because you can just diagonalize. But you can, so we of course need it for NP oracle. And the point of making this sort of like assumption is that now you get hidden set generators and PRGs with very small seed lengths. So a theorem under hardness assumption. So one, there exists explicit PRG with seed length or a log n. Against time for all k, against time n to the k with log n bits otherwise. So basically, like what we can do with this hardness assumption is to get arbitrarily small seed length for a serial generator, except that now, like the adversaries you fool are going to be like almost uniform adversaries. They're only going to have a small amount of non-uniformity. So this way, you kind of are exploiting the fact that you're fooling uniform algorithms rather than non-uniform ones. And second is for all n, put infinitely many n, so let's not worry about what n seeds are. There exists explicit PRG for all d, PRG with seed length. For log of the d. So iterated logarithm d times against time n to the k, where say iterated logarithm d minus 1 times. But the point is that we don't really have like any advice in the adversaries that we're trying to fool in our explicit construction, so we don't care too much about the advice. We just care more with the uniform time bound. And yeah, it turns out that you can make the seed length really, really small if you're fooling uniform algorithms. And once you do this, then like the method we had before of just enumerating the range of the PRG and concatenating, or there's an additional kind of trick that you can do. This gives you strings of high time order complexity, and from that explicit constructions. And thereby you get evidence for explicit constructions for the problems that we discussed before. I'm going to share more time to discuss at least the high-level proof of this, but yeah, feel free to ask me about that, the questions. Yeah, thank you. Thank you. Sorry.
So could you summarize? So is the following a relatively accurate summary of what happened? We had constructions of PRGs, their appropriate hardness assumptions before. We noticed that we could use those PRGs to basically fool tests that will give us construction of rigid matrices or objects like that. But that was not enough because the seed length of these PRGs was large enough. It wasn't enough to give us list constructions with anything reasonable on the bound on the list side. So So this theorem is like, so it replaces that PRG construction with a PRG construction with significantly smaller seed length.
Yeah.
And then we plug in into the same machinery, and we end up in a situation where the seed length is now so small that the entire image is something that's the size of that is.
Yeah, I mean that's somewhat hard. If you want more hardness, you get like infinitely often hardness by like doing a different trick. But essentially you're leveraging very small seed length, and like the interested only in pseudorandomness, not in explicit constructions at all. This is essentially a way to get optimal seed length against slightly non-uniform adversaries. So it gives you a generator, yeah.
And adversaries, so adversaries like this are enough for some of the constructions.
For all of constructions, yeah. I mean, the adversaries are all uniform. So the question is, how do you exploit the uniformity of the adversary with a natural hardness assumption to get explicit constructions? And so that's what's going on. And basically, the idea is to kind of recursively compose PRGs by using these strong hardness assumptions.
Yeah, two questions. So one is regarding construction of these PRGs. Do they just happen by taking the standard IW PRGs and doing them iteratively?
Recursing on the
Recursing on that. Two, so there's been this other line of work in PRGs in which you get you use PRGs de-randomized DPP, but you don't use any overhead in time. That is, and the one way of possibly doing it is the seed length was epsilon log n, then it's consumable. So will such a line help you to
I mean, our work might help to improve that potentially, right?
No. So will this actually help to do? Are there? I don't see it right now because the advice is a bit too little over here. They have to full things which are larger advice.
Yeah.
So is there a version? But I don't want it to be so small. The seed length, epsilon log n seed length is fine. So is there a version of this which will actually imply their theorems?
Yeah, that's a good question. Not completely sure about that, but I mean, if you have like super fast renormalization, let's just say for like tally languages, and you want to work for infinitely many n, then this would give you a stronger result somehow. So it's closely related. You could potentially take this and like an appropriate hardness assumption, and I mean, essentially they have like this bottleneck of epsilon log n because of their setting, but we don't have the bottleneck because we are fully uniform algorithms, and so that allows us to get much smaller seed length.
Responsible for the name